Hello class, this is chapter 2 for Intro to Anatomy and Physiology Bio 101. In this chapter we are going to be talking about chemistry. So you're probably wondering why I'm taking a biology class or I'm taking an anatomy and physiology class. Why do I need to take chemistry? Well, unfortunately or fortunately, chemistry is the basis of biology. Everything in biology happens because of what we understand about chemistry. If you remember back to chapter 1 when we were talking about the different levels of organization, remember a cell is what is considered a living thing. That's a basic unit of life. Everything below that is what the cell is made of. So the cell is made of organelles, and organelles are made of organic molecules, and that's chemistry. And organic molecules are made up of simple atoms and molecules. That's chemistry as well. Plus, water is a really important part of biology and anatomy and physiology. So our body is roughly 70% water, and so understanding water and how it works and all that sort of stuff, that's really important as well. That's also chemistry. And then the other big topic is pH. So we'll be talking about just general chemistry. We'll talk about organic chemistry. We'll look at pH as we go throughout this lecture. If you've had chemistry before, that's great. Hopefully this will just be a review for you. If you haven't had chemistry before, really take some time and get down into this material and try to help it make sense and get help if you need it. I'm happy to answer questions and kind of help you out there. But I think maybe one of the biggest things with chemistry though is this problem that it's abstract. So the things we're going to be talking about now, atoms and how atoms are made up and things like that, we can't see that under a microscope. It's so small that we don't have any pictures of this. We have drawings and things like that of what we think it looks like, and don't get me wrong, this is it's all been tested and experimented on, and this is how things work, but we don't have any exact pictures of what these things look like. So that may make it kind of difficult for people to understand. But here we go. So chemistry, the first topic here, the first thing to define is this idea of matter. Matter is anything that takes up space and has mass. And you've probably heard that before. All things are made of matter. Not just living things, but non-living things as well are made up of matter. And there's three states of matter. There's solid, liquid, and gas. Great example is water. Water is one of the few types of matter, molecules, that is found in all three states naturally on Earth. So we have water in a gaseous form, which would be steam. We have liquid water running around, and then we have solid water, which is ice. So those are the different states of matter. All different types of matter can have those different states, but some of them aren't found naturally because it has to be too hot or too cold or different things in order for those to happen, and you don't have those conditions on Earth. Now matter is made up of elements. This is when we get into the chemistry. There are 92 naturally occurring elements. Naturally occurring meaning that they're found on Earth naturally. There are other elements that are not natural. And so the question is, well, how do you have a non-natural element? Well, a non-natural element is one that scientists can create in the lab, but it's still all of them are so unstable that they only last for a brief period of time before they break down. So we have 92 naturally occurring elements. And if you go to the resources in your book, you'll see, not online in Blackboard, you'll see what's called the periodic table of the elements. Now this has all 92 natural elements, so it goes clear up here to 88, and then you can see it jumps down here, and you have some of these others in this thing down here. 92 is uranium, which you've probably heard of. That's the last of the naturally occurring elements. All these others that have these kind of funny names, these are the ones that are not naturally occurring. And there's a whole bunch of them, and scientists are still creating more elements for whatever reason. So, but the ones that we're familiar with, and the ones that we are going to spend most of our time talking about, are gonna occur up here. So we are made of matter. We're a living thing. We're made of matter. We're made of elements. The interesting thing about us is that we are really only made of 4 main elements. All of our body, all of the different molecules and everything in our body is only made of 4 main elements. Let's see if you can guess what they are. One is hydrogen, one is carbon, one is nitrogen, and one is oxygen. So 1, 2, 3, 4. So those 4 right there make up the majority of all of the things inside our body. And these letters here are a single letter that represent what these elements are. So O stands for oxygen, N stands for nitrogen, etc., etc. All of these elements either have a 1 or 2-letter symbol that represents that element. And that's true across all of science. So these are set in stone, I guess. It's the way to think about that. Okay, so this is a chart that shows these different elements and how much of life is made up of these. So these ones are the important ones. We just talked about these 4 top ones. There's a couple others that are really important in life, phosphorus and sulfur. And then these elements here also are important to life, but they don't necessarily make us up, but they're important in our body functions and things like that. Sodium, magnesium, chlorine, potassium, calcium. Calcium is part of us. So our bones are mostly made of calcium, but because it's not one of the main ones, it is an important element in our body, but it's not one of the main 4. Even though we think, oh yeah, we're made up a lot of calcium, we're made up more of these 4, but calcium plays an important role. I don't know if that makes sense, but that's kind of how these things work. Okay, so all of these elements are made up of things called atoms. Now, atoms are the smallest units that you can break something down into, and it would still have the physical and chemical properties of that element. So, for example, if you have, I guess I have a gold ring here. It's made of gold. Now, this is made up it's made up of gold, which is an element. So if I was to take this ring and break it down into its pieces, I could eventually break it down into individual gold atoms. And those atoms would still be gold. So they'd have the properties, even though it'd just be a single atom, it'd still have the properties of gold. We can't see an atom, it's so small, so this ring is made up of millions of atoms of gold that have come together to form a ring. And each of those atoms have the same physical and chemical properties, and they come together to form this ring, which has the same physical and chemical properties. We can break atoms apart, but once we break them apart, they're no longer. So, for example, if I take that gold atom and I break it apart into its little pieces, it's no longer going to be gold. It's not going to function as gold. And that's true of all of these elements. So all of these elements on the periodic table of the elements are pure. These are the basic form of these different substances. So atoms can be broken down into smaller structures, and this is what they're made up of. And if you've ever taken chemistry, you've heard of these. If you haven't, you may or may not have still heard of them before. But atoms are made up of 3 main particles called protons, neutrons, and electrons. Now these are the building blocks of atoms. So protons and neutrons, in other words, protons, neutrons, electrons come together to form atoms. Let's go back to the gold idea. So you have these, gold atom is gold. It's made up of a certain number of protons, neutrons, electrons. If we were to break those apart or change the number of protons, neutrons, electrons, it's no longer going to be gold. So for example, carbon, which is one of the major biological atoms, it has a certain number of protons, neutrons, and electrons, and it's represented by this little diagram here. This is what I was talking about. This is what an atom might look like, because we can't see it. This is how we draw an atom. We know that atoms are made of protons, neutrons, and electrons, and each type of atom, each element, has a specific number of protons specifically. So carbon always has 6 protons. And this is just a unit that they're made of. This carbon atom also has 6 neutrons, and if we count them, 1, 2, 3, 4, 5, 6 electrons. Now we call this carbon 12, and we get that number from the number of neutrons and protons. Okay, so let's back up a little bit and see if we can make this all make sense. Now I'm just kind of throwing numbers at you and things like that. So let's do it this way. So let's go to the periodic table and look at carbon, because this is important. If we go to the periodic table, we see that carbon has a number of 6. Now each of the numbers on the each of the elements on the periodic table has a number associated with that. That number never changes. In other words, carbon is always going to be number 6, nitrogen always number 7. If we go down and look at gold, gold is always going to be number 79. that never changes. That element, that's why this is called the periodic table of the element, that element always has that number. Now that number tells us something. That tells us how many protons a certain atom has. So carbon always has 6 protons. That's what makes it carbon. So you can see here, here's our protons, and there are 6 protons in carbon. Carbon will always have 6 protons. If we were to take this drawing and put 7 protons, this would no longer be carbon. We come here and look at the periodic table. This would now be nitrogen, which has 7 protons. So the number of protons is determined by the periodic table, how many protons that atom has, that type of atom. Now the neutrons and the electrons are a little bit different. They're going to be determined by some other things. Let me tell you that number, I didn't mention this, but that number on the periodic table, this is called the atomic number. The atomic number of an element never changes. Carbon always has atomic number of 6. Okay. Now the number of neutrons is determined by something we call the mass number. Now the mass number is equal to the number of neutrons and protons. So the mass number for this carbon atom is going to be 12. Because in this drawing here, in this carbon atom, we have 6 protons and 6 neutrons. Now the number of neutrons can vary. And we'll talk about that here in just a minute. The number of protons never does, but the number of neutrons can vary from one carbon atom to another. So in this case we have carbon 12, that's the mass number. The mass number is equal to 6 protons to 6 neutrons. So if we know the mass number and we know the atomic number, we can figure out the number of neutrons, because we take the mass number minus the atomic number, which is the number of protons. That gives us the number of neutrons. Now the number of electrons, now this in order to understand the number of electrons, we have to understand something more about protons and neutrons. Protons and neutrons and electrons have charges associated with them. So what they have here is, so protons always have a positive charge. I was going to try to draw a plus sign there. It's not letting me. Anyway, protons always have a positive charge. Neutrons, so think of neutrons, they have no charge, and electrons have a negative charge. So protons positive, electrons negative, neutrons 0 charge. So if we have an atom that has 6 protons and there is no charge associated with the atom as a whole, then we know that the number of electrons are going to be equal to the number of protons. Because once again, the protons are positive, the electrons are negative. So if there's no charge on the atom, then the number of protons and electrons have to cancel each other out. Okay, so hopefully this is all making sense. If not, we need to practice this just a little bit. But first, let's define some things here. So atomic number. So the atomic number is what? Give you a second to think about it. The atomic number is the number of protons in an atom, whatever that atom is. That atomic number never changes. Carbon is always 6, gold is always 79, etc. Okay, the mass number, let's get rid of this here. Let's just say the mass number is equal to the number of protons plus the number of neutrons. Now why is this called the mass number? Well, these little particles actually have a mass. They're matter, they have mass. And this mass is measured in units, very, very small units. So the mass of a proton is just about 1. And then the mass of a neutron is also about 1. So the number of protons and neutrons together equal the mass of that atom, which in the case of carbon would be 12. If we come back to the periodic table, the mass number is listed with each of these elements. So carbon has an atomic number of 6, has a mass number of 12, 12.00011 in this case. We just round to the nearest whole number, which is in this case is 12. Nitrogen has a mass number of 14, etc. So the reason that it's not an exact number is because there can be variations. So in this case, the main type of carbon is carbon 12, meaning that there are 6 protons, 6 neutrons. We can also have carbon where there are more neutrons, either 7 or 8 or something like that. another thing to look at here is on the periodic table. So the atomic number is listed here above the letter. The mass number is listed under the letter. Now when I showed you, let's go back to carbon, when I showed you carbon on this PowerPoint, it was actually opposite. So when we write out the element, we write it as it's shown here on this PowerPoint. So there's going to be the C for carbon, and to the lower left, the subscript will be the atomic number, and above it will be the mass number. When we look at the periodic table, it's actually switched. The atomic number is always going to be on top, the mass number is on bottom. Why did they do this? Why are there two different ways? I don't know. But you can always figure out which one is the atomic number, because the atomic number is always going to be equal to or less than the mass number. So if you look at the periodic table, the atomic number is 6, carbon with the carbon 12, so the atomic number is 6. If we write it out, same thing, even though the atomic number is below, it's the lower number, and so it's the atomic number is always the lower number. Okay, so where do we go from here? So now we know the atomic number, we know the mass number, we know how to find those, we know how to find the electrons. So let's do a test here. Let's test you and see how you do. So if I give you, for example, oxygen, let's say oxygen, and I'm going to write it like this, oxygen 16. Okay. And so if we were to write this out, this is how this is going to look if we try to write this out. So we're going to have carbon, let me grab my thing here. Okay, hold on, let me get this for you here. Okay, sorry, now here we have oxygen, and we're going to have oxygen, hold on, I'm sorry, let me do this again. So we've got oxygen here, and okay, sorry about that. Here we go. So oxygen, here's the written out. So oxygen has 8 and a 16. So what I want you to figure out is, what is the atomic number, what is the mass number, what is the number of protons, what's the number of neutrons, and what's the number of electrons, based on this idea that there's no charge here on this oxygen atom. So go ahead and pause this recording, try to figure that out, and then we'll come back and I'll tell you the answers. Okay, hopefully you tried this and you were successful. So let's go over the answers. So first, the atomic number. What is the atomic number? Atomic number is 8. Remember, that's always the lower number. And that's also the number of protons. So there are 8 protons in this oxygen atom. So then what's the atomic mass? The atomic mass is 16. Remember, the atomic mass tells us the number of protons plus the number of neutrons. So if the atomic mass is 16 and there are 8 protons, then that tells us that 16 minus 8 is going to give us 8 neutrons. So then finally, how many electrons would there be in this oxygen atom? Well, the number of electrons, in this case there's no charge, and we have 8 positive protons, 8 neutral neutrons. So to cancel out the 8 positive protons, that means we have to have 8 negative electrons. So there are 8 protons, 8 neutrons, and 8 electrons in this case for this example. Okay, I'm going to give you another example. Hopefully you got that. Let me give you another example and see how you do here. Okay, here it is. So it's also oxygen, but something has changed. So see if you can figure out, again, the atomic number, atomic mass, number of protons, neutrons, and electrons. Okay, welcome back. Let's see how you did. So the atomic number did not change because this is oxygen. Atomic number is always 8, which is equal to the number of protons. There are 8 protons. What did change is the atomic mass. It's now 17. So we know the atomic mass is equal to the protons plus the neutrons. So 17 minus 8 equals 9. So there are 9 neutrons. Electrons, we still have no charge. So the number of protons, the number of electrons are going to be the same. So there are going to be 8 protons, 8 electrons. Now we have a name for this situation. These are both oxygen atoms, and they just differ in their atomic mass, or in other words, in the number of neutrons. We call these isotopes. So two atoms that have the same atomic number but have a different number of neutrons, we call those isotopes. Isotopes are very important. There are a number of different isotopes, and going back to the periodic table, that's where we get this change in mass, is by the number of different isotopes, because this mass is an average of all the different isotopes and how common they are. One that you may have heard of before is what we call carbon-14. So carbon comes in carbon-12, carbon-13, and carbon-14. So carbon-12 is the most common, and it's not radioactive. Carbon-13 is also it's a heavier isotope. It has 7 neutrons. And then there's carbon-14. The interesting thing about carbon-14 is it now becomes a radioactive isotope. So I bring up this example because you've maybe heard of carbon dating. Okay, carbon dating is a way that scientists try to figure out how long ago something lived. And they do that by using these radioactive isotopes, carbon-14. And they compare the amount of carbon-14 to the amount of carbon-12 in an organism. Carbon-14 is radioactive, and basically what radioactive means is it's unstable, so it breaks down over time. So when we think about radioactivity, we think of danger and things dying, which is true. So radioactivity in high dosages kills living things, but in low dosages it doesn't do as much harm. So we are exposed to radioactivity every day. There's carbon-14, which is radioactive in our environment. It's actually in our bodies as well. As we consume food, we are bringing carbon-14 inside our body. And the ratio of carbon-14 to carbon-12 in our body is maintained throughout our life as we continue to take things into our body. However, when you die, the amount of carbon-14 is then set because you're no longer eating. And so then it'll start to break down over time. So what scientists do is they come in, they look at the amount of carbon-14, and they figure out how much is there, and by figuring that out, they can figure out when that individual died or that organism died, because they know how long it's taken for that amount of carbon-14 to break down. So there are other things that we use radioactive isotopes for, especially in medicine. One of the things we use them for is X-rays. And all other tests like mammograms use radioactivity. So that's why X-rays can be dangerous in high dosages. We also use them for tracers. In other words, what we do is we give radioactive substances to patients to consume, and then we can watch them as they go throughout the body by measuring that radiation. So we can see how things are working in the body, or we can focus in on certain parts of the body like the thyroid using radioactive iodine or things like that. So those are things that we use them for. We can also use radiation to sterilize things. So for example, UV radiation can kill things in high dosages, so we can take that radioactive substances and we can use that to sterilize equipment. So these are some uses of radioactive isotopes. Some elements are always radioactive. So for example, uranium, any isotopes of uranium are going to be radioactive, and that's because it's such a large atom that it's always unstable. It's always going to break down over time. Some of these others, carbon, nitrogen, oxygen, normally their most common isotope is not radioactive, but as you add in more neutrons, it eventually gets bigger, becomes unstable, becomes radioactive. So there's radioactive carbon, there's radioactive oxygen, there's radioactive hydrogen, etc., etc. So those are called isotopes. Okay, so let's go back and do one other example here. And here it is. So take a look at this. So the thing that has changed this time is there's now a charge associated with this atom. So turn off the video, try to figure this out, and then turn it back on and we'll go over it. Okay, welcome back. So what changed here? So the atomic number is still the same, it's 8, which means that there are 8 protons. The mass number is the same as this one, meaning that there are 8 neutrons, because 8 protons plus 8 neutrons equals 16. So the thing that is different here is the number of electrons. So this time we have a negative charge. So we have to figure out what does that mean. So we have 8 protons which are have a positive charge. So we basically have 8 positive charges on this atom. But overall the atom has a negative charge. So that means that there has to be more negative things offsetting these positive things by 1. So there's no 1 written here, but if it's just a negative sign, then the 1 is assumed. If it has a number, then that tells you how many negative charges are. So if there are 8 positive charges on this atom, then there must be 9 negative charges on this atom to give it a negative charge in total. So there are 9 electrons. So 8 protons, 8 neutrons, and 9 electrons. Now when an atom has a charge, this charge can either be positive or negative depending on the type of atom. We have a name for this as well, and we call this an ion. So an ion is when an atom has a charge, and that charge is caused by either gaining or losing electrons. So remember, protons can't change, but neutrons can. That becomes an isotope. And electrons can change, and that becomes an ion. If an atom has a positive charge, we call that a cation. If it has a negative charge, we call that an anion. Okay. So, all right. So now you are able to figure out, hopefully looking at the periodic table, or by being given an example, you can figure out the number of protons, neutrons, electrons. You know what the atomic number is. You know the atomic mass. So now what we need to talk about is bonding, and how atoms come together. And this is where electrons become important. The number of electrons in an atom become important. So atoms form together to form molecules, and different molecules can come together to form what we call compounds. So bonding is all about the number of electrons. So let's look at how the electrons can vary in an atom. To do this, we're going to come back to this picture of the atom with the electrons written around. So in an atom, the electrons that are in that atom they are floating around or running around a central nucleus. The nucleus is made up of protons and neutrons. Electrons are in this, what they call a cloud, around the nucleus. But within that cloud there are certain energy levels. The first energy level can only hold 2 electrons. Once it has 2 electrons, it's full. And any electrons beyond that are going to have to be in the next energy level. The next energy level can hold up to 8 electrons, and then it's full. And then after that, the electrons will go to the next energy level. Now these numbers that these energy levels can have become important. So 2, if an atom has it only has 1 energy level, and it has 2 electrons in that energy level, then that atom is going to be stable. It's going to be happy, or however you want to think about it. If it has a second energy level, it needs to have 8 electrons in order to be happy. So if we're looking at carbon here, carbon has 6 electrons, 2 in the first level, so that's full, and then we put the last 4 in the second level. Carbon only has 4 electrons in this outer level, which we call the valence shell, but it needs 8 in order to have that shell be full. So this is where bonding comes in, because the way that level can become full is if carbon was to gain or lose electrons or share electrons with other atoms. Okay, so this is this whole idea of bonding. Bonding is all determined by the electrons. So let's go down and look at some different types of bonds. Let's go back here. Let's start with ionic bonds. So ionic bonds are caused by an attraction between 2 elements that have charges, or 2 atoms that have charges, and then they just attract each other. So a great example here is sodium and chlorine. Now if we were to look at sodium on the periodic table, here's sodium. There are 11 protons, and the atomic mass is 22, so there are 11 neutrons. In a neutral state, it has 11 electrons. So if we were to draw the sodium atom here, those 11 electrons, 2 would go in the first shell, 8 would go in the next shell, and that is full, and that would be 10 electrons. So the last electron would go into a third shell, and it's hanging out all alone. Now this third shell also wants to have 8 electrons to be happy or stable. So this last electron is making sodium unhappy. I guess I was talking about as terms as happy and not unhappy. But anyway, that electron is making it so it's not stable. Chlorine, if we look at chlorine over here on the periodic table, atomic number is 17, which means if there's no charge, there are 17 electrons. So when you fill up the chlorine shells, the last shell has 7 electrons. It's missing an electron in its non-charged state. So it wants an electron to finish off that 8. So where can chlorine get an electron? Well, it could steal this electron from sodium, and then it would have 8 electrons in its outer shell. Now chlorine, because it just needs 1 electron, it is very reactive. It reacts with basically anything because it's trying to pull that electron from wherever it can. So when it pulls that electron from sodium, it then has 8 in its outside shell, and because it now has 8, it now has 18 electrons, which means that chlorine now has a negative charge. When it steals that electron from sodium, sodium now has 1 less electron than it did, so it now has a positive charge. Positive and negative attract, we get what's called an ionic bond, and this is how salt forms. So sodium and chlorine come together to form crystal salt. Something else to point out here is this interesting idea in chemistry. When you have 2 elements that come together and interact and bond, they form a new substance that has different properties than the 2 substances themselves. So in this case, sodium is actually a metal. And it's a metal that when you put it in water, it can even explode. It's reactive. Chlorine is a poisonous gas. However, when we put them together to form an ionic crystal, we call this table salt, which is not poisonous and it's not a metal. So a very different substance when we bond things together. Okay, another type of bond. Oh, let me point out this word electrolyte. Electrolyte is a fancy word for salts. So you may have water that has electrolytes in it. That has different salts in it. The next kind of bond is called a covalent bond. Now, a covalent bond is different than an ionic bond because in a covalent bond, atoms are sharing electrons. They're not stealing or giving up electrons. Okay, so in this case, we can have different types. This sharing, covalent bond can have can share a different number of electrons. Sorry to stumble through that. We have single bonds where they're just sharing 1 pair of electrons. Double bonds are sharing 2 pairs or triple bonds. So let's look at how this can happen. So we have oxygen and hydrogen. So if we looked at oxygen again, on the periodic table, oxygen has 8 protons, 8 electrons. If we fill out the shells, 2 in the first, and oxygen is going to have 6 electrons in the outer shell. So it wants 2 more electrons to be happy or stable. If we look at hydrogen, hydrogen is number 1, meaning it has 1 proton and 1 electron. So it actually it only has 1 shell, so it only needs 1 more electron to have a full shell and be stable. So if oxygen and hydrogen come together, what they can do is they can share electrons. So hydrogen shares its electron, oxygen shares its electron. So now if we look at this, we have 1, 2, 3, 4, 5, 6, 7, 8 electrons in the outer shell here. And then hydrogen has 1, 2, and this hydrogen has 1, 2. We've now formed a covalently bonded molecule called water. Here's another example. This is nitrogen. Nitrogen has 7 protons, 7 electrons. So what can happen here is we can have, so let me go back. Nitrogen is going to have 5 electrons in its outer shell, so it needs 3 more. So one of the things it can do is it can bond with another nitrogen, and they share 3 pairs of electrons, forming a triple bond. A triple bond. So each pair here is a single bond. So here's a single bond, here's a single bond. In this case, we have a triple bond. And what that does is it makes it a very strong bond. A triple covalent bond is very, very strong, very hard to break. And so that's what's going on here with nitrogen when they're bonding with each other. That's covalent bonds. Those are the 2 main types of bonds, ionic bonds and covalent bonds. There's a slide on the PowerPoint, there's a little animation that I encourage you to look at that gives some information or shows how these ionic bonds and covalent bonds happen. And that's where we're going to end here. This was a little bit longer video than I'd like to do, but hopefully you stuck through And next we're going to talk about water, acids, and bases in a new video.